Welcome back to another video. This is Machine Learning by Tom and Mitchell. I'm going through pages 63 through 68, um, where it talks about the inductive bias in decision tree learning. Basically, the bias is that shorter trees for ID3, shorter trees are preferred over larger trees. And this goes in concert with Occam's razor that states prefer the simplest hypothesis that fits the data. So those two go hand in hand. It also goes into the difference between a restriction bias and a preference bias. So ID3 searches a complete hypothesis space. Basically, it is capable of expressing any finite discrete valued function. It doesn't search the entire space, but it's capable of representing the entire space. Whereas the candidate elimination algorithm searches the whole space, but the space is incomplete, meaning there could be the target function that the target function could be outside this space. And that's the difference between a restriction bias and a preference bias. The preference bias is a preference for certain hypotheses over others that don't have a restriction on what can be represented. Whereas the restriction bias restricts how you can represent the target function, or represents your representation of the target function, but it doesn't have a bias on a particular type within that space over another. And in general, you would prefer a preference bias over a restriction bias because, at least in the preference bias, you know for certain that the target function can be represented in that space. With the restriction bias, the target function you're looking for could be completely outside the space. You'll look at all the options, but none of them could be good, basically. So there's that. They also go into the example that there are algorithms that could have both a restriction bias and a preference bias. So, for example, the example where you're trying to teach a program to play checkers against a human world champion, there's a preference bias. There's a restriction bias because you represent it as a linear function. So nonlinear functions are excluded, so it's not representing the whole space. Also, at the same time, the choice of the parameter tuning method, which was the least mean squares algorithm in this particular case, introduces a preference bias because you're preferring to represent the tuning in that way. It's still going through the space of all popular parameters, but that's the one that you prefer, from what I understand. Then it goes into Occam's razor, like arguing whether or not the simplest hypothesis is necessarily the best. It doesn't really give a solid thing one way or the other. It just gives you both sides of it. And then it comes to issues in decision tree learning, basically you don't want to overfit the data, and it describes overfitting the data as if you have an algorithm that performs really well in the training data, you have an alternate hypothesis. It's said to overfit if that alternative hypothesis fits better the entire distribution of instances. So the training plus the test, better than your original algorithm. So there's that. Then it goes to a new example for that. Yeah, and that's pretty much. Oh, it goes into noise, like if there's noise in the data, what overfitting, like if you overfit, what problems that can cause. That's pretty easy to understand. And then before the end, I mean, I'm about to end this video, but you can avoid overfitting in two ways. You can either stop growing the tree earlier before it reaches to the point where it perfectly classifies the training data. Basically, you don't allow it to get down so specific to every training example. Or you post-prune, so you let it get down to those specific examples, and then you look at each level in the tree and you prune the tree accordingly to the best accuracy, which ID3 does not, I don't think, allows you to do, or maybe there's a version of ID3 that allows you to do it. I don't know. So that's it for that video. Hopefully that was helpful. It was definitely helpful to me, and I'll see you in the next one.